Algebra 2, welcome back. I am actually doing this as sort of a, refresher on simplifying square root radicals. And then, since I won't actually be here for first and second and fourth hour, I'm recording this on behalf of the sub, who I understand is Mrs. Bryan. So I understand she looks harmless, but trust me, you're going to want to do what she says because I don't want to get fired. So let's do this, right? Okay, so you remember that this theorem here, so we have x, y. If we're going to take the square root of that, that's going to be the same, identically, to xy to the 1/2. These mean the same thing. Taking something to the 1/2 is taking the square root of it. It's the same idea. And this, as you know from that property that you guys all aced on the test, is going to be x to the 1/2 times y to the 1/2. We can be careful about using the word distribute, but that's essentially what we're doing. We're multiplying this exponent to both of these elements inside. So this is going to equal x to the 1/2 times y to the 1/2. And since we already know that taking something to the 1/2 is the same as taking its square root, this is going to be identically equal to square root of x times the square root of y. So this whole thing is just to show that the square root of x times y is the same thing as the square root of x times the square root of y. Now the same holds true if you're doing higher roots. And the way we denote a higher root is to, first of all, this is an implied 2 right here. We're taking a square root. We're taking the number you have to multiply. This is something you'd have to multiply by itself twice to get xy. If we're going to take the cube root of x times y, this would be the number that you'd have to multiply by itself 3 times in order to get xy. So the same pattern holds. This is going to be identically equal to xy, not to the 1/2, but to the 1/3, by that rule that we learned last week, actually a couple weeks ago. And this is going to be identically equal by that property of multiplying the exponents. This is going to be x to the 1/3 times y to the 1/3. And taking something to the 1/3 power is the same as taking its cube root. So this is going to be identically equal to the cube root of x times the cube root of y. So this all just goes to show you that the same principle holds. In fact, we could generalize this. Xy, the eighth root, I should say the nth root of xy is the nth root of x times the nth root of y. It holds true no matter what type of root we use. So let's use that idea to try and figure out how we would break down a cube root or a fourth root or a higher order root. We did squares, now we're going to do cube roots. The same thing holds true. Let's say we're going to try and find the cube root of 54. Okay. Well, remember, when we were doing prime factorization on a square root, all we're doing is breaking this up into the smallest bits possible, and we're looking for pairs. Well, since we're taking a cube root, we need a perfect cube instead of a perfect square. And that would be a number that would be the product of another number multiplied by itself 3 times. So let's see if we can break this up into pieces here. Let's see, 54 is 2 times 27, and then 27 is 9 times 3, so that's 3 times 9, and then 9 is 3 times 3. So you'll notice that this section here, 27 breaks down to 3 times 3 times 3. In other words, it's a perfect cube. So its cube root can come out in front of the radical. So we're actually looking for groups of 3 instead of groups of 2. And just like on square roots, any numbers that can't find a group of 3 stay inside the radical. So we have one group of 3's, so that's going to come out of the radical as a 3. So this is going to equal 3 times the cube root of whatever didn't make it out, which is the 2. And in a more general form, the cube root of 54 equals the cube root of 2 times 27. And we just showed that 27 is a perfect cube. It's 3 cubed. So this is going to be equal to the cube root of 2 times the cube root of 27. And we just showed that the cube root of 27 is 3. So it's going to be the cube root of 2 times 3, or 3 times the cube root of 2. So it's the same principle that we were doing before, except now instead of finding pairs like we were doing with a square root, we're finding groups of 3 with a third root. And then anything that doesn't make it outside stays under the radical. Anything that does find a group of 3 makes it outside the radical. Let's try that. Let's try the fourth root. See if we get this. So the fourth root of, let's do a perfect fourth root. Let's do fourth root of 64. And let's throw some variables in there. Why not, right? Same principle holds. Let's say 64x to the 5th. Okay, so let's break this down into the smallest bits possible. Let's see, 64 is 2 times 32. So we replace that with 2 times 32. 32 is 2 times 16. 16 is 2 times 8. And then 8 is 2 times 4, and then 4 is 2 times 2. And then let's break down this x. Well, x will just break down into x to the 5th breaks down into x times x times x times x times x. Now, since we're dealing with a fourth root, let's keep the pattern the same. With a square root, we're looking for pairs. With a cube root, we're looking for groups of 3. And you guessed it, if we're doing a fourth root, we're looking for groups of 4. They need to be in a group of 4 to escape the radical. So we have 1, 2, 3. We have 4 2's here. That can escape. And looks like we have 4 x's here that can escape as well. And what's left inside that didn't escape is this lone x. And then we have a pair of 2's here. And there's unfortunately nothing we can do with this pair of 2's. We need to be in groups of 4 to escape a fourth root radical, right? So let's figure out what escaped and put that in front of the radical. The group of 2's escaped, so we have a 2. A group of x's escaped, so we have x, and then what didn't escape was 2 times 2. So let's do the fourth root of 2 times 2 is 4, and then we have a lone x that didn't escape either. So hopefully you get the idea of what we're doing when we do higher order roots. It's the same idea that we're doing with the square roots. It gets a little bit trickier because it gets kind of hard to remember. You can remember perfect square numbers pretty easily. You get 9 and 16 and 25 and 36 and so forth. It gets a little bit more tricky to remember higher order roots. But let me just give you a couple that are worth remembering. So we have, let's do the squares first. 2 squared is 4. 3 squared is 9. 4 squared is 16. And 5 squared is 25. So if you notice that if we're talking about a square root problem, if you notice that any of the numbers are divisible by 4, 9, 16, or 25, that's a gimme, because we can just divide it by that number and then chuck these numbers out as their square root. Let's do 2 to the third equals 8. 3 to the third equals 27. And 4 to the third equals 64. And 5 to the third equals 125. And fourth roots get very interesting. Let's see, 2 to the fourth is 16. 3 to the fourth is 81. And 4 to the fourth ends up being 256. It's pretty rare that you'll see terms that are divisible by numbers this big. Really, the one you're going to want to look for is in cube roots, 8 and 27 are good numbers to try and divide by. And then if you have fourth roots, really 16 is about as big as you're going to get. It's pretty rare you'll see 81. You certainly wouldn't see 256 very often. So these are the numbers to kind of keep in mind. If you're doing square roots, you're going to try and divide the numbers by these numbers to get a perfect square. If you're dealing with cube roots, we want to try and divide. Your first try is going to be to divide by 8 or 27 to see if you can get a perfect cube that you can check out of the radical. And fourth roots, 16 and 81 are the numbers you're going to look for to see if you can chuck something out of the radical there. So hopefully this helps, and go ahead and dive into the worksheet, and I will see you tomorrow. I've also posted, as usual, the solutions to the worksheet. So good luck, and I will see you on Wednesday. Take care.